All right, let's see. Continuity with limits. Again, the definition of continuity, right? Is it defined? Does the limit exist? And therefore there's a left and the right-hand limit and they're equal to each other. And then lastly, that limit must be equal to f of c, or the function's height at that same value. So let's get into it. Here we got a little bit different question than we've seen before. This one's just asking, does the limit as x approaches 2 of f of x exist, and is it continuous? Well, let's just think about this real quick. If we had some, let's say we had some function that went like this, and then there was a line function here, right? And let's say it did something like this. Well, these don't match up, right? And so if I was evaluating the limit at, let's say, a, obviously this limit wouldn't exist, the general limit wouldn't exist because the left and right-hand limit are different, right? It's also not going to be continuous, because if you're riding this roller coaster is going to suck. You're going to fall off the edge of this. Is bad news. But what if I change it? What if I just move this line down a little bit so that it meets up perfectly? Now, not only is it continuous, but the limit is going to equal each other. So really, they're kind of asking the same thing. If the limit exists, then it's going to be continuous, as long as we're evaluating it, you know, at the point where the function breaks, and we are here. See, we're evaluating the limit at as x approaches 2, and that's when this piecewise function is separated right at 2. So let's give this problem a try then. Now that we know that, that means then that these two things need to line up, right? These functions need to line up. So their limits, the limit basically as x approaches 2 from the left of f of x has to equal the limit as x approaches 2 from the right of f of x. If that's true, then the limits are going to connect, right? Or the functions are going to connect perfectly. Can't really get them to touch here, but they're going to connect perfectly, and the function's going to keep going continuously. It's not going to have any holes or anything like that. So let's go ahead and evaluate this, right? So the limit as x approaches 2 from the left, well, from the left is going to be when x is less than 2. So this is going to be negative 2x plus 6. And we're just going to set that equal to, and actually we're asking, is it equal? Is really what we're doing here. So we're going to see if it is equal. We're going to set that equal to the limit as x approaches 2 from the right. And on the right, we're going to use when x is greater than 2, so we're going to use this guy. And so we're just going to evaluate these. Let's see. When I can just plug it in. There's no reason why I can't just plug it in. So if when I plug in a 2, I get negative 4 plus 6. And then that gives me positive 2. So is that equal to the right? Well, on the right here, there's no reason why I can't just plug it in. So let's plug it in. 2 squared is 4. And 4 minus 1 is 3. So is this equal? No, it's not. So does the limit exist? No. And therefore, this only means therefore, it is not continuous. Yeah, my handwriting sucks. All right, let's go to the next problem. All right, so this one's a little bit different here. It says, for what value of a is the function continuous at x equals 0? Okay, so we've done this kind of problem before. Again, remember, if it's continuous, then the limits are going to be equal. And so the limit as x approaches 0 from the left of g of x is going to equal the limit as x approaches 0 from the right of g of x. And so we have the limit as x approaches 0. What is to the left of 0? Well, it's when x is less than 0, so it's this guy. So it's 4 sine x over x. And does that, again, we're just kind of asking, does that equal the limit as x approaches 0 from the right? And now, on the right of g of x, that's when x is greater than or equal to 0. And that's going to be a minus 2x. Oh, my bad. Actually, we're not asking if it's equal. We're setting it equal, so you can erase this. We're setting it equal because we're going to find out what value of a makes it continuous. So we're going to actually say, yeah, let's go ahead and set them equal, and let's solve. So let's do the left. This is pretty easy. There's no reason why I can't just evaluate this. This is one of my rules. I can't just plug it in, right, because I get something over 0. But this is one of my rules, this sine x over x. So a way of rewriting this is 4 times the limit as x approaches 0 from the left. Oops, I don't need the 4 there anymore. Of sine x over x. Well, this whole thing we already should know by now. That's just 1. So 4 times 1 is just 4. Okay. This one, there's no reason why I can't just plug in a 0, because there's nothing being divided by 0 or anything like that. So I really just have a minus 2 times 0. Well, 0 times anything is 0, so a minus 0 is just a. And so now we have found out that a has to be 4. Okay. Okay, the u-try problem here is a little bit different. I want you to just pause the video, give this one a try, but I do want you to add something to this. I want you to also ask yourself, and is it continuous? Because you do have enough information to answer that question. So think about those two things, finding the limit and is it continuous, and then we will check back after you've paused and given it a try. Check back and we'll go over the problem together. Okay, hopefully you've given it a shot, but let's talk about it. First of all, if I'm evaluating the limit, all I'm really asking is, as this thing approaches 1, does it equal the same thing? Well, look, as it approaches 1 from either side, we're going to just be using this function. And there's no reason why we would have a hole or anything like that in this function. So the limit exists, and it's going to be really easy to find because this point right here is only true for that value at 1. But here we're just asking what the limit is as we approach 1. So we really only need to do the limit as x approaches 1 of x squared plus 5. Well, that's really easy. We could just plug in. That's just going to be 1 plus 5, and so that's 6. Okay. But then I told you to also answer this question, is it continuous? So to kind of explain this, let's go ahead and just kind of sketch this thing real quick. What would this look like on the graph if we remember that it's not this parabola when x equals 1? Well, this is just a parabola that's up 5 units, so just make that a 5. It just looks something like this. With a hole right here at 1. So that's all this would look like. But then they're telling us when x is 1, what do we do? We're going to go to 3. So let me just put a little 3 here. And so there the graph just kind of jumps down there like that. We got a little removable discontinuity because we just removed that point. Okay, well, now we can tell it's definitely not continuous because there's a hole here, and this point doesn't fill the hole, so then it just, if you were riding a roller coaster, you would just kind of fall through, right? So this is not continuous. We got this gap here, and it's not filled in. But what if this problem, instead of having a 3 here, had a 6? Well, that would mean that this hole is filled with the same value that we're approaching, right? As you get closer and closer to 1 on this graph, we found out that, yeah, you're getting closer and closer to 6. So what if this thing said, hey, when x equals 1, you're actually going to make it be 6? Well, now you have that hole filled, and so now this graph is continuous. Keeps going on and on forever. So just kind of a little interesting problem there, a little interesting way to think about it. Hopefully that helps. We'll see you guys on the next video.